Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at analysing a scissor lift. All right, so let me share my screen and we'll get into it. All right, so here is the problem. Let's read through it and make sure we understand everything that's being asked before we dive into it. So we've got the scissor lift here. Scissor lift mechanism consists of two sets of cross members. So we need to be careful of making sure we analyse it accordingly. And we've got two hydraulic cylinders. So we've got a platform here. So two sets of these cross members. So one on this close to us and one further away behind that we can't see. So we need to take that into consideration, and we're told the platform has a uniform mass of 60 kilos with a centre of gravity at G1 here, and the load of 85 kilograms with a centre of gravity of G2 as shown here, centrally located between each side of the platform. So then we're asked to determine the force in each of the hydraulic cylinders down here, bottom right of the picture. So yeah, we need to determine the force in the hydraulic cylinders for this to be in equilibrium. And we're told that we have rollers at B here and D. Okay, so let's work our way through. So we're just going to analyse one side of the platform. So we're going to divide these weights into half for the analysis. So we're going to assume that the weight is evenly distributed, and of course we're going to draw a free body diagram to start our analysis, but we need to think about what are we going to draw a free body diagram of. Often this is the most difficult part of machine analysis in engineering mechanics. So I'm going to draw a free body diagram of the whole frame, because that has our known loads in it and also our unknown force in the cylinder that we're looking to find. And then let's see how we go with solving the problem with just that free body diagram. I think we're going to need more than that as we go through. So we've got the loads here, W2 and W1. I've just labelled them rather than putting the numbers on here on my free body diagram. So now we need to look at where this machine is connected to other things and where we've disconnected it, or imagine that we've disconnected it, and we're now looking at the forces that are acting. So down here at point D, we've got a roller support, so just a vertical reaction there, and then we've also got the force exerted on the scissor lift by the hydraulic cylinder. So that's going to be a two-force member. So it's only connected at D and E. So we know the direction of that force. I'll leave the arrowheads off for now. We'll put them on later. Then over here at F, at the connection to the ground for this other part of the scissor mechanism, we've got a pin connection here attached to ground. So we've got horizontal and vertical reactions there. So let's start thinking now about our force sensors. So the force from the ground onto the roller or the wheel here of this scissor lift, I think can easily see that it's going to be acting upwards here. We can also just imagine that we take moments about point F here, and if these two forces are causing a clockwise moment about point F, then the reaction here at D must be causing an anti-clockwise reaction for equilibrium. All right, so let's move on to the next one. So if we, again, we've got the weight acting downwards, this is probably going to be acting upwards for equilibrium. We can do the same thing that we did just before. Imagine that we take moments about point D here. These two forces are causing an anti-clockwise moment about point D. So the reaction here at F must be acting upwards to cause a clockwise rotation about D for equilibrium. And then the hydraulic cylinder, I think we can imagine and see that we need to push on the roller here, D, for this to be staying up where it is, or to push these weights up even further. Okay, so that's fairly clear. And then on the other side over here at F, sum of the forces in the horizontal direction equals 0, so this one must be opposing the one over here on the right at D. So let's give them all some labels so we can use them, so that we can refer to them in our equations of equilibrium. So I'm just going to call this dx and dy at point D here, and fx and fy. All right, put on some dimensions on our free body diagram so that we can refer to those when we're calculating the moments or determining the moments of all of the forces. And we're given the masses of the platform and the crates or the load in kilograms, so we need to convert that into weights in newtons, so we've multiplied by gravity, 9.81 meters per second squared. So starting our analysis, usually we'll start with the moment equation, because typically we'll be able to have, sorry about my phone going off in the background there. Typically we'll have two unknown forces going through a single point at a pin connection like this. So if we take moments about that point, then we can find our other unknown from that one equation. Okay, so I've said here, sum of the moments about point F and anti-clockwise is positive, all equal to 0. And then we can start to write that out. So we've got W2 here, its perpendicular distance, line of action, perpendicular distance to point F is 0.8, as we can see here on our neatly drawn diagram. And it's tending to cause a clockwise moment about point F, so that one will be negative. So let's go on to W1, so the weight of the platform itself, perpendicular distance of the line of action of the force from point F, where we're taking moments about, is 0.8 plus 1.2, so that's 2, and it's again clockwise about point F, so negative. And then we have the y here, down the bottom. Perpendicular distance to point F is 1.5 plus 1.5, which is 3, and it's tending to cause an anti-clockwise moment about point F. So that one is positive. They're the only things causing moments on our about point F on our free body. So we can now make that all equal to 0. Do some rearranging. So what I'm just going to do here, because we've got dy on the other side here, and the two weights, I can just put 9.81 out the front and then multiply by the masses. And I've divided by 2 because we've got 2 sets. Okay. So the load is half the load is distributed on each side. Yeah, so just put those numbers into this rearranged equation, divide by 3. Okay, so just this 3 here comes onto the other side of the equation, and we can solve for dy, do our maths, and we get 307.38 newtons for the vertical reactions at dy. So we can't find dx yet because we've got 2 unknowns and only one equation. Right, so I've just redrawn the free body diagram over here on the next page. You don't need to redraw it. It will still be there on your piece of paper or iPad, tablet, whatever you're using to work on. So I've just written there for reference so that I don't have to keep flicking backwards and forwards to other pages. So the next equation of equilibrium is sum of the forces in the vertical direction equals 0. So we can put all those in. So we have Fy, dy that we found before here, and the 2 weights that we know. So we can rearrange that equation and solve for our unknown vertical reaction force at F. Do our maths, and we get 403.8 newtons. All right, so I haven't actually gone and written in the horizontal force equation here because I can see that I'm just going to get Fx is equal to dx. and I don't know either of them yet. So now, in order to work out dx here, I'm just going to draw another free body diagram. So this time I'm going to draw a free body diagram of just the platform and see how I go with that. So there's the free body diagram of just the platform, and now I need to think about the reactions at the support. So now I've taken away the cross members of the scissor lift and replaced those with the forces they exert. So at A here, it was a pin connection. So we've got horizontal and vertical components of that reaction force. And then at B, we were told that was a roller connection here. Right? So go back and look at the question to see that. I'm not going to flick back. All right, so that's our free body diagram. So now just put on that extra dimension there. Look at the sense of these forces. So if we imagine that we take moments about point A here, these two forces are acting downwards to cause a clockwise moment. This one needs to cause an anti-clockwise moment for it to be in equilibrium. So that's why that one's acting upwards. And then over here, you can do the same thing again. Take moments, or imagine you're taking moments about point B. These ones are causing an anti-clockwise moment. So this one needs to cause a clockwise moment for equilibrium. So that one's pushing up. If you can't do this, thinking through this in your head, you can just assume a sense of these forces, and then your algebra will tell you whether you got it correct or not. Okay? If it comes out negative, then it tells you that the sense of the force that you put was incorrect. But never go back and change your free body diagram. Right? Just leave it as negative. Okay, and then I put in here, even though we can see that this horizontal reaction force is going to be 0 because there's no other horizontal loads, I've just put it in here for completeness. And label all of our forces so that we have something to refer to in our equations. So now I can write some of the forces in the x direction, or the horizontal direction, positive equals 0. So I can see and write here that AX equals 0, as we discussed. Then take moments about a point. So usually take the moments about the pin connection, right, because the moment of these two things is 0. So we can find BY directly. We do that, we have BY times 3, tending to cause an anti-clockwise rotation about point A. So that's a positive one. And then we have W2 times 0.8, tending to cause a clockwise rotation about point A, so it's negative. And then W1 times its perpendicular line of action, perpendicular distance is 2, and again, clockwise, so it's negative. All equal to 0. We can solve for BY. Again, I just put 9.8, 1 out the front there, and do our maths, and we get 307.4 newtons for BY. Okay, so now if we do some of the forces in the vertical direction equals 0, AY plus BY minus the two weights, rearrange the equation, and we get 403.85. All right, so then we can go to the next page, I think. Right, so yeah, I've just copied across my free body diagram again. You don't need to redraw the free body diagram. You should have it already drawn. And also I've copied across the free body diagram of my platform. And from before, we had AY equals FY equals 403.845, AX was 0, BY equals DY equals 307.38. So now if we draw a free body diagram of ACD, which is one of the cross members, all right, again, we've got the dimensions on our free body diagram, and then start to put on our loads. So AY here, the load on this member must be equal and opposite to what we had down here on the free body diagram, so the bottom left-hand corner of the page here. That AY there acting on the platform So this is the force that the member ACD exerts on the platform. Following Newton's third law, action and reaction pair, the force over here on point A of the member ACD must be equal and opposite to that. Okay, so this is the force that the platform exerts on the member CD. At point D, we have our what we drew before, so we can put those back on there, being consistent from what we had from our original full machine free body diagram. And then at C, we've got a pin connection at C between the member ACD and the member FCB. So there we'll have horizontal and vertical reactions. Put some labels on those. We're not actually going to calculate those in this example, but if you're doing this as an actual design problem, then you would need to calculate those. All right, so now that we have our complete free body diagram, we can start to use our equations of equilibrium again. All right, so taking moments about point C, because dx is what we ultimately want to know. We already found dy before, but for the textbook problem, dx is what we want to know. So we can take moments about C, and if we do that, we have, I've shown the full equation there, so let's work through it. So we have AY times 1.5, so perpendicular distance from AY's line of action to point C is 1.5, and it's tending to rotate anti-clockwise about point C, so positive. And then we have down here dy, perpendicular distance from its line of action to C is 1.5, and again tending to rotate anti-clockwise about point C, so positive. And then we have dx, its line of action, perpendicular distance to C is 1, and it's tending to cause a clockwise rotation about point C, so it's negative. Okay, so they're all the moments about point C for that free body diagram, so we can rearrange that, do the maths. So I just left out a line here, but all I've done is just substituted AY that we found before and dy that we found before into here and solve for dx. All right, so now that we have that, we have a final answer for the textbook problem anyway. So our final answer, the required cylinder force is 1.07 kilonewtons. Okay, and I've just included on the next page, as I was saying before, if this was a design problem and we need to specify the sizes of all the lifting mechanism components, then we'd need to draw free body diagrams and complete all the equations of equilibrium to find everything in the problem, right? So we need to know the forces here at Cx and Cy, so we know the forces on the pin connection. And then if we were going to size this member, it would be in bending. Right? So we need that in order to properly size that structural component. Okay, so that's the end of that problem. Hopefully that was helpful and interesting to you. The problems are becoming a bit more authentic and real looking than just the previous chapter in the textbook that's just rigid body equilibrium. But as hopefully you can see through how I've solved this problem, I haven't introduced anything new beyond just the basic or fundamental rigid body equilibrium problem and method of solving those types of problems. You just need to be disciplined and careful with drawing your free body diagrams, be consistent through your working, and make sure you're obeying Newton's third law when you're looking at the forces where you've disconnected parts of the machine or frame that you're analysing. Anyway, that's it for now. See you next time. Bye.